Hello everybody and welcome back to a new video. This week we are continuing in our module that covers acoustics. So last week we talked a little bit about what acoustics are and kind of just touched on a basic introduction of acoustics and how they work. This week is going to be a little bit more focused on acoustic applications within designs and how we look at actually implementing solutions for acoustical problems whenever we are working as interior designers. Your reading for this week is going to be that same ballast reading I have posted on Blackboard. So if you didn't read it last week, make sure you take a look at that this week, and then also Chapter 8 from the Bengali textbook. All right, so let's go ahead and get started. Our engineers, architects, and interior designers each play a role in the implementation of acoustical solutions within a building's design. All right, so all three of those people, engineers, architects, and interior designers, they're all going to play a role in the acoustics when it comes to the building design, but it's going to be at varying levels, and they're all going to have different focuses within the project. All right, so an engineer and an architect would focus more on the structure of the building and the mechanical components and things like that that are within the building that are making noise. Okay, and noise transmittance through the structure of the building itself. Whereas an interior designer would focus more on the actual rooms within the building interior and how those individual rooms are handling sound control. All right. There are 4 areas of concern when addressing acoustical issues. So we have room acoustics, sound isolation, mechanical equipment, and sound systems. Interior designers are primarily concerned with room acoustics. This means they focus on the acoustical environment within a space as well as the isolation of sound within and between spaces. All right, so both of those are big things. How does the quality of the sound within a space that you're in sound based on the application of the space? So if you're in a lecture hall, how good does the quality of the person who's speaking voice sound when you're sitting inside of that space? Or if you are in a concert hall or like a theater somewhere where music is playing, how good is the quality of the music within that space? How does it sound to you? And then also the transmission of sound between spaces. So as an interior designer, there are going to be specific strategies you're going to want to implement in order to prevent sound waves from transmitting between 2 separate spaces. Okay, so for example, if you're in an office, if you're in the work environment as opposed to a conference space, you want to stay focused. You don't want to hear what's going on in the conference room next to you. So we're going to have to find ways to prevent the sound from leaking out of the conference space and getting into the work area where people are trying to focus. All right, so acoustic design. When designing for existing buildings, interior designers must determine the cause of sound problems so they can implement an appropriate solution. All right, so we're in an existing space and we're doing some kind of a renovation to that space, and maybe there's a known sound issue. As an interior designer, we're going to want to pinpoint the source of what is causing that sound issue and then come up with an appropriate solution in order to correct whatever the problem is. All right. But when we are designing for new buildings, we need to imagine what noise sources can be anticipated within that space, okay? So let's say we're working on a project for a new ground up building. So nothing is built yet, but we can use some maybe observations in order to tell what kind of acoustical needs we will have to consider for the final design of the space. So for example, the building site, is it located in a noisy area? Maybe it's downtown or something and there's a lot of traffic that's going to be going by. That's something that we could anticipate for. Or actually, what's the function of the space? So is it going to be a theater or a lecture hall or an office, something that needs a lot of sound isolation? All of those things are going to help us in determining what we are going to need for the project based on the use and also the location of the building. So acoustic requirements for each individual room should be reviewed to develop an effective sound control strategy. Again, each room within the building is going to need different things. Okay, so the sound and acoustical requirements for one space is going to be probably different than another space depending on what its use is. Noise sources should be placed as far as possible from quiet areas. Okay. When you're working on projects professionally, something that you might encounter is acoustical consultants. So these are people who you may bring into a project based on a specific need. So, for example, if there's a project where loud noise is a special problem or where interior sound is critical, you may contract an acoustical consultant to handle the sound control strategy for the design. It is common to use an acoustic consultant for projects such as performing spaces, educational spaces, and libraries. All right, so basically, a typical project, you will not need to bring on an acoustic specialist. It really just depends. Like, for example, what the notes were saying, if you have a space where acoustics is a really big deal, keep going back to performing halls and things like that, things centered around sound and music, that's when you're going to want to bring somebody in who specializes in those applications, because they're going to have a much better idea than you on what kind of strategies can be used to make the sound quality within the space as effective as possible. All right, so it's something that you may encounter, but it's not necessarily going to be, or these people won't necessarily be used for every project that you work on. Acoustic consultants play a role in the selection of interior materials and the detail of construction components. Their work has direct implications on the work of interior designers. All right, acoustic modeling. So acoustic modeling is basically specialized computer software that you would use to simulate the acoustic levels within a space before it's built. All right, or maybe it is a space that is built that's being renovated and you're adding a bunch of things in the building and you want to see how that is going to impact the space. You could use acoustic modeling software to get an idea of what the sound levels within that space are in order to help you implement a more effective acoustical design strategy within your design. All right. Now, this isn't something that is commonly used for a lot of projects, just like a acoustical consultant. This is more so a tool that an acoustical consultant or a sound specialist would have in their arsenal when approaching a project. So, the software that we're going to be using professionally as designers typically won't have these features built into them. And again, this is something that is more specialized, all right? Room acoustics. So the behavior of sound within a space depends on the shape, size, and proportions of a room. The behavior of sound is also impacted by a room's contents, such as the finishes and furniture within it. All right. So we mentioned this last week. As interior designers, we're mainly focused on what is within that space and how are the things within the space interacting with the sound waves that are being produced. Okay. In spaces with high levels of sound reflection, sounds are mixed together and it becomes more difficult to discern one sound source from another. When steady sounds are mixed together, they reverberate, resulting in a noisier space. Okay, so reverberation, that's a term that we talked about last week. That's basically the persistence of sound. When a sound wave goes out from the source, it wants to bounce around, and the reverberation is basically the amount of time that the sound is staying active, that you're still hearing it after it's reflecting. When steady sounds are mixed together, oh no, I just said that. Reverberant spaces can make music sound better, but they can also cause speech to become less intelligible. All right, so I kind of touched on this last week. Reverberation isn't necessarily a bad thing. It really just depends on, again, the use of the space. So if it's a space that's meant for music and performing arts, you want to have some reverberation because it can actually enrich the sound and make it sound a little bit grander. But if it's a space where you're just hearing people speak, then you want to minimize the reverberation because it can make it more difficult to understand the speech of the person who's talking. All right. In spaces that have high sound absorption, speech becomes clear, but music may sound worse. Acoustic fields. So most enclosed spaces have 3 different types of acoustic fields. We have a free field, we have reverberant fields, and then we have reverberant fields with absorption. So a free field, this is basically when you're in a space and sound waves can go out and disperse uninterruptedly. So this is more toward like maybe the center of a room where there's no obstructions, all right, and the sound just kind of like goes out without being affected by anything that it's hitting. A reverberant field is when sound waves are multiplied and interwoven. So these kind of areas exist at the perimeters of rooms and also in the corners. Basically just the areas where sound waves are bouncing around, okay? And then a reverberant field with absorption is basically the same thing as just a regular reverberant field, but these are areas where we have some kind of absorptive material maybe applied to the surface, and that is absorbing some of those sound waves and causing them to reflect less. All right, so if you think back to last week, I mentioned we're going to be treating surfaces with special materials that are going to reduce the way that these sound waves are being reflected. All right, so again, these types of areas, maybe places that have soft furniture or some kind of special acoustical material applied. Acoustic reflections and openings. So in spaces such as lecture halls, theaters, and concert halls, an effective sound control strategy is absorbing sound waves at the first point of reflection. Right, so if you've ever been in a lecture hall or a theater or something like that, and you've noticed the acoustic panels that they've had installed, or the design of the space when they went ahead and installed those panels and laid them out is actually thoughtful, and it's usually done with a specific reason, the location of them. So they don't really just put them everywhere they possibly can. Really, the idea is you want to place these panels in the spot where the first bounce is going to occur, because if you can kind of kill the sound wave at the source, then there's not really a need to have them everywhere else, okay? So through using like modeling and things like that to determine where these bounces are going to occur, you can put the acoustical treatment in that location so that it just stops the sound wave, from the very beginning. So it just hits it once, it gets absorbed, and some reflectance occurs, but it's a lot less than it would be. All right. So it's going to be common to place absorptive materials or acoustic panels toward the sides and also the backs of these spaces, these larger spaces, to catch the sound waves before they can bounce around the space. Reflections off of hard polished surface. So these are known as specular reflections, all right? So remember that term. If you hear a specular reflection, that's just saying it's bouncing off of something that's really hard and usually polished. Building noise control. So there are 3 basic ways to control noise within a building. First is reduction at the source through proper selection and installation of equipment. All right, so what is producing the sound? Can we use some kind of a strategy where the sound is coming from in order to reduce its impact on the space? Reduction along the paths of transmission through proper selection of construction materials and construction techniques. So this has to do with the actual building itself and reducing the ways that sound is being transmitted through the structure. All right, so sound waves create vibrations, and those vibrations will interact with the actual structure and the building assemblies, and they will kind of move through the structure and transmit between the spaces. So, we can actually use specific construction techniques to kind of mitigate the transition rate through the structure itself. And then lastly would be more in line with what we're doing as interior designers, which we've been talking about, and that's controlling the noise through the selection of acoustical treatments within specific spaces that need them. So controlling exterior noise. Penetrations within a building's envelope will allow exterior noise to come through into the building's interior. Obviously, right? We don't want holes in the building's exterior shell that would allow any sound sources to get through from the outside to the inside. There are several design strategies that can be implemented to prevent unwanted outside noise from coming indoors. So window and door openings can be oriented away from sources of undesirable noise. You can't always do this, obviously, but it just makes sense if you have no openings on the face of a building where there's going to be a high level of noise. Maybe there's a really busy street out there or something, then obviously the noise is going to have less spaces to penetrate through the building envelope. But again, it might not always be practical to do that. It just really depends on the situation. Windows with multiple layers of glazing are going to block noise more effectively than those with a single layer of glazing. So whenever we're specifying windows or any type of fenestration for our buildings, right, in our designs, we want to lean towards those which have multiple layers of glazing, again, because more layers is going to block the transition more. And we should be doing that anyway for energy conservation reasons, right? But just an added benefit is that it's going to also be blocking sound waves a little bit better and have better acoustic properties. Interior spaces can be screened from the outside by using mechanical service and utility areas as sound buffers. All right, so we may have regions within or outside the building that are acting as service cores, and the placement of interior spaces, you can kind of use those service cores to your advantage, because those will create a natural barrier or a buffer space from the outside noise to the inside. So you can also think of that whenever you're designing as, do I need a quiet space or in one particular area? And if I do, can I use some of these systems within the building that are already occurring as sort of a natural screen that's going to block that noise from getting to the interior? Activities with higher noise levels should be located on the noisier side of the building. So that's pretty self-explanatory, pretty obvious. I don't know, let's say you have a recreational space and maybe you have a gymnasium or something. There's going to be a lot of noise in there. So if there's a side of the building that tends to be noisier, maybe it's like, again, a busy street or something like that, whatever side that street is on is where you would probably want to locate those noisier spaces. And then maybe you had like a childcare area or like a nursery. You're going to want that to be a quieter space, so then that would be placed further away from the noisy areas, okay? Airtight building assemblies are effective at blocking noise. Any unnecessary holes or gaps within the building envelope should be covered to block sound transmission. All right. So going with that, one way that we can do this and make our building construction assemblies more airtight and less likely to transmit sound is by using acoustical sealant. So this is like a special caulk that can be used at the edges and joints of building assemblies to reduce sound transmission. Here you can see is a little example of somebody installing it. So this is them actually using it on an interior wall assembly. So it looks like they just put up some gypsum wallboard, and then at that intersection there in the corner, they're putting some of this sound blocking acoustical sealant, and this is specially formulated to kind of seal it up really tight so that no sound waves can make their way through those small cracks between the joints there. And then also lastly, in addition to thermal benefits, weather stripping on windows and doors can block unwanted noise from entering a building through small gaps around doors and windows. Okay, so I think we touched on weather stripping a little bit, maybe like a few weeks ago. But again, just like multiple layers of glazing, if we have weather stripping installed, that's going to create another just sort of natural block against sound transmission through small gaps and things between doors and windows. All right, so now controlling interior noise. So noise within building interiors can also come from the activity of building occupants and the operation of building services. Okay, so the people within the building are going to be making noise. That's going to be the primary sound source, but then you also have maybe mechanical equipment or some sort of the building's providing a service. Anything that utilizes that service is probably going to be making some level of noise. So interior designers should locate spaces that need to be quiet away from areas that have a lot of mechanical equipment, such as service cores. I kind of mentioned, here on the last slide that you may use these mechanical areas as like a sound buffer. So that can be an effective strategy, but it really depends on like the use of that space. If it's something that is really sensitive and really has to be quiet, maybe you don't want to locate it as close to a service core as you would a place or a space that doesn't need that high of a level of acoustic consideration. All right. And then sound transmission. So sound can pass through spaces around. It can pass through spaces around partitions, and it can also transmit through the partitions themselves. And to combat this, designers can specify thicker or double partitions for spaces that need to be isolated from exterior sound sources. These partitions should be full height, extending from the floor to the structural decking of the floor or roof assembly above. All right, so if we look at these diagrams here, these are taken from the textbook. First of all, this one here is showing you can have two spaces that are separated, but the sound can actually transmit directly through a wall. So if there was let's say there's no gaps or anything, like this is totally airtight and there's no small gaps where it can like get around this partition, it can actually go through the partition itself, right? So if you think about being like in an apartment or something and you can hear your neighbors next door, or maybe you've tried to eavesdrop on somebody by putting a glass against the wall and then putting your ear up to the glass so you can hear the sound better. That's sort of how this is working. So any sound, no matter how airtight the space, is going to want to travel through the partition itself. Okay, and some sound is going to get through. So to combat that, you're going to want to consider the design of these partitions between spaces so that you're minimizing the transmittance from one to another. So a way to do that is, like I said, you could have a thicker partition, or maybe the partition is constructed in such a way as to where it has acoustically treated materials within it. Maybe you have insulation inside of that partition that is actually absorbing some of the sound as it's making its way through the partition. Insulation doesn't necessarily have to be used for thermal purposes, like on a building exterior. We can also use insulation within the interior of a building for acoustical reasons, and that's something that you're going to commonly see as you're designing. If the space really has to have high acoustic performance, you might see them using like batt insulation within walls on the interior just to block sound waves from getting from one space to another. All right, and then this one down here is showing how sound waves can actually get around partitions. So, in commercial spaces, you might have these situations where partitions don't extend all the way up from the floor to the decking above it. They may just go up to the ceiling, and then you might just have open plenum space above it. Well, wherever that occurs, the sound waves are going to want to kind of travel up through the ceiling and then go over top of the partition, right? So we want to make sure our partitions are extending all the way up to the very top to that deck above so that we can minimize the transmittance over top of the partition itself. All right, so flanking paths. This is basically just to reinforce the point that sound waves can transmit from one space to another using several different paths or in several different ways. And usually they're going to take the path of least resistance. So if you look at this diagram here, these are just a bunch of examples of all the different ways that sound can get from one room to another. So here you can see it's going up through this diffuser and it's actually making its way through the ductwork. That's one of the most common ways that you're going to have sound transmittance. So, you probably experience this now, maybe at your house. I know I do. You could have somebody in one room talking, but maybe you are upstairs or in a different part of the floor, and you can hear their full conversation because it's actually going through the vents from one room and it's making its way to the other room through the ductwork. Okay, so that's a very common one that you'd run into. And then also, like I was saying, it can go over to the top of walls, or it can even go underneath of walls if there's a gap there anywhere. Again, it can also go through the partitions itself. All right, so these are all things that we have to take in consideration. Maybe at first glance, the idea of like isolating sound sounds pretty simple, but when you start to think about it, you're like, oh wow, there's actually all these different areas where a sound can make its way from one area to another, and you have to think about that and think of ways that we can prevent that from happening. All right. Sound absorption. So the sound absorption performance of material is going to depend on its thickness, its density, porosity, and its resistance to airflow. So installation of absorptive materials. installation methods are very important in determining the effectiveness of an absorptive material. All right, so we have a few diagrams here that were from the textbook. So if you look, you can see we have here is a heavy solid barrier. Below that is a absorbent material and heavy solid barrier. So it's just the barrier with an absorptive material on top of it. And then below that is just the absorbent material only by itself. So when we just have the solid barrier, when we have a sound wave coming in, it's going to reflect and it's going to maintain almost all of its strength as it's reflecting off of the surface. And then the portion of the sound wave that is transmitted through that barrier is going to be relatively weak. So when you're on the other side of that partition, you're not going to hear very much. Now, I'm going to go down here to see when we have a strong sound wave coming in and impacting something that's absorbent, the sound wave is going to maintain its strength pretty much all the way through that material. So if we had a space and it was divided by, some kind of fibrous acoustic material, and that was acting as the partition, if you had somebody talking on one side of it and then you had somebody on the other side of it and they were listening, most of the person who's talking's sound is going to make it all the way through that material. But then not much of that sound is going to be reflected off of that material, okay? So the idea is it prevents sound from bouncing, okay? So it's reflecting, it's not really reflecting off of it all that much, but it's not really doing too much to prevent sound from transmitting, okay? So what we want to do is use the two in conjunction with one another. So here you can see in the middle, right, we just took the absorbent material and we put it over top of the solid barrier, and that is kind of doing both things that we want it to. So the sound wave's coming in, it's leaving as a weak reflected wave. This is actually a typo that they have in the book that should say weak, not strong. But the sound wave isn't really bouncing around as much because the absorbency of the material is going to weaken it. And then also, because we have this solid barrier behind it, that is going to prevent transmission through the assembly. So it's going to make the acoustics within the space where the sound is coming from sound better. And then also on the other side of the wall, you're not going to get as much transmittance and you're not going to hear as much what's going on in the other room. All right, so now if we look over here at these diagrams, these are basically illustrating the installation of an acoustical sealing treatment within a space. So the least effective thing that you could do is take whatever that material is. So let's say this is acoustic ceiling tile. We're going to talk a little bit more about that here in a minute, but let's say we have acoustic ceiling tiles. The worst thing that you could do with those is attach them directly to any structure that is above it. So let's say this gray here, this is just like a floor joist or something like that. What we don't want to do is nail it or glue it directly to that floor joist, because if it's in direct contact, it's going to provide a better way for this sound to actually be transmitted into the structure. A better thing to do is to have some sort of like a blocking that is suspending that slightly below the structure, because you're not having as much of a surface area behind these acoustic panels in contact with the structure itself. It's just this small area here that is in contact, so not as many of the sound waves are going to be making their way through the structure. All right, but the best thing to do, and this is going to be the most common thing, especially in commercial spaces, is using these ties to suspend your sealing material from the structure itself. So that's typically what they do when they install these sealing grids. They're going to have wire that is attached to them, so you can see these little loops, and it's holding up the sealing grid with this wire. that's going to go up to the structure, and it's going to be fastened here into the structure. And basically what that's doing is it's creating this big air gap. And if we remember back to thermal properties, air gaps are good for insulation. They're also good when it comes to acoustic treatment. So if you have like sort of a dead air space between two surfaces, that's going to act as a way to prevent transmission of sound waves, okay? So any sound that does get in here and is transmitted through the material, it only has this thin little wire to make its way through. So really it's hardly even getting to the structure at all. It can only travel through these small wires, and at that point that really just cuts down so much on the amount of sound that would even be transmitted. All right, so this is going to be the best way to approach a ceiling installation of an acoustic treatment. So now to finish up, we're just going to touch on a few different acoustic products. This is the last section I'm including in the notes, but the textbook goes a lot more in depth about acoustic products and also different ways that sound is being transmitted through spaces. So make sure you're reading the whole chapter, because I may pull things from that for your quizzes coming up. All right, but this is the last thing we'll talk about today. So ceiling products. The ceiling is the most important surface to treat for sound absorption. All right, keep that in mind. Most important is the ceiling. The most common product used for ceiling acoustical treatment is acoustic ceiling tiles. Okay, so as opposed to just a drywall gypsum wallboard ceiling, depending on the space you're dealing with, you might want to consider using acoustic ceiling tiles, because that is going to usually be your best way to control sound within the space from a ceiling perspective. So acoustic tiles, these are excellent absorbers of sound within a room. Usually they're going to be placed in a 2x2 or a 2x4 metal grid, and as I said on the last slide, these grids are usually going to be suspended from the structure above for acoustic reasons. That being suspended also in and of itself is an acoustic consideration. They can be easily removed to allow access to plenum spaces. All right, so very simple, just pop off a tile and then you can stick your head up there and do whatever you need to. So they're really convenient in that respect. They're available factory painted or with ceramic, plastic, steel, or aluminum facing. So there's a lot of different options when it comes to designing. A lot of times, people may think an acoustic ceiling might look ugly, but there's a lot of products out there on the market right now that are actually like really cool looking, and there's a lot of different ways you can customize them. So if you don't want to go with something that's super basic and traditional, there's all kinds of options. There's these metal ones that look really slick. You just have to look at them. For example, if you were to go to Armstrong's site, they are the biggest manufacturer of acoustic ceiling products, and they have all kinds of stuff that you can use for your projects going forward, all kinds of Revit files and things, but that's going to be one of your best sources for any kind of acoustical ceiling treatment. So you should check out what they have. If you look at this, or these two images I have here, so this is basically a better look at how a acoustic ceiling system is going to be suspended from the structure above. So you can see we have this little bracket that is nailed into the joist, and then it has a wire that runs through it that is going to be hooking into the ceiling grid below. All right, and this wire, the distance can be adjusted, okay? So you can see right now it's actually pretty close to the joist itself. It's not suspended down very far, maybe an inch or two, but you can actually adjust this and make the ceiling drop lower and lower based on whatever needs you have. And then if you look here, this diagram is kind of showing the same thing, but what I wanted to show you here is just like we can put insulation within a wall cavity to prevent sound transmission, a lot of times, say you need a really high rated acoustical performance for a space, You might even throw some insulation above the acoustic ceiling tiles. So here you can see they just take rolls of bad insulation and they just lay it in there over top of the ceiling tiles. Okay, and that's just going to add an extra layer to catch any sound transmissions that would be going into that plenum space. So the next product would be perforated metal pans and panels. So this is kind of what I was talking about with like the Armstrong products. These are basically a metal panel that is backed by an acoustical filler, and they're going to be used on ceilings and walls to absorb sound. Okay, so if you look at this one here, this one kind of mimics like a wood grain. Okay, and they just have these tiny little slots in them, and then you can integrate, just like a normal acoustic ceiling tile ceiling, you can integrate lighting fixtures and you can integrate diffusers for your HVAC system, and they're pretty cool looking. Usually it's pretty minimal in their appearance, and it's kind of just a cool way to integrate all these building systems into the ceiling and also have good acoustical performance. Acoustic baffles, these are another kind of cool looking thing that you can implement into a space to increase the acoustical performance. So these are just sound absorption devices that are suspended from ceilings. So if you look in this picture here, all these like crisscrossing shapes, these are the baffles, and they come in all kinds of different shapes and designs, but they're just kind of cool because they're performing a specific function in terms of absorbing sound waves, but they're also providing a lot of depth and visual interest to the ceiling itself. All right, so it can actually be used for kind of a focal point within your designs. Acoustic clouds and canopies. So these are basically the same thing as baffles, except they're just kind of flat planes. Usually they are made of acoustic ceiling tiles themselves, but you can see these are just circular kind of clouds that are suspended below the plane of the metal decking there. And again, used for sound control, but they have just a layer of visual interest to them. They can also be used, you might just like use one or two over specific areas. So maybe you have a space that needs, it's a space within a larger open space, and that particular area needs to have good sound control. So you could just maybe take one of these clouds and just suspend it over top. Maybe it's like a cafeteria space within like a larger space. You could just put one of those little clouds over it to help control the sound within that open environment. And then wall panels. So these are the kinds of acoustic treatments that you're going to be seeing in like lecture halls or bigger areas. And these are just panels that are attached to the wall. Acoustic wall panels have wood or metal backings and mineral fiber or fiberglass substrates. They're used in offices, conference rooms, auditoriums, teleconferencing centers, and educational facilities. And just like baffles and things like that, these don't have to be boring looking. They usually, you just see them in rectangular configurations. They're just rectangles that are being screwed to the wall, and that could be kind of boring looking. So they actually offer a lot of like really cool designs that you can take a look at. But again, like in spaces like this that would be otherwise really plain or boring, you can actually use the acoustical treatment to create sort of a focal point and make the actual space more interesting. All right. And then lastly is carpet. And carpet is the only floor finish that can be used for sound absorption. All right, so any other floor finish is going to reflect sound waves a lot. Carpet is the only thing that you can use on a floor that will absorb sound in a reasonable way. Carpet with padding under it will absorb more sound than carpet that does not have padding. So again, this just makes logical sense. If the carpet is thicker and it has a foam pad underneath it, it's going to absorb more of the sound waves than if the carpet was just installed directly over top of concrete or something like that. All right, so that is going to do it for this week. Make sure you read the chapter. Like I said, the chapter goes a lot more in depth on certain topics, and there's a lot of things I just didn't include in here. A lot of it is repetitive, right? And a lot of it is common sense as well. So that's kind of the reason why I kind of pared it down and didn't include all those things. But sprinkled in there, there's going to be some things that I just didn't discuss, didn't get to in this lecture. So make sure you take a look at the readings and see everything that they were talking about. That's going to be it. If you have any questions, as always, please reach out to me and I will get back to you.